Alright, so I'm going to go ahead and I'm going to write down both of the equations that you're going to really need to know when it comes to motion, and we're going to talk about them briefly. The top one is called the time dilation equation. It's saying that our experiences in time changes depend on a point of view. The bottom one is our length contraction. Same principle, the exact same idea, the exact same procedure, but instead of solving for t, we end up solving for length, and we end up getting this equation. It's the same procedure. It's the same fundamental idea. I just didn't want to go through all that math to get the solution for that. So what Einstein is saying with these equations, that is our way we envision the universe depends greatly on how fast we're traveling. The passage of time here is different depending on the situation. I mean, if you look at it, the question you get is that why don't we see this relative motion at all? I mean, why don't we see relativity on a daily basis? Well, if you look at the equation, you look at the bottom term on that time dilation, 1 minus v squared over c squared. The only way that you're going to get any kind of representative or any kind of observable data from here, the observable time dilations, is if your velocity is probably in the same order as the speed of light. So you're talking about tremendously fast speeds. As a matter of fact, we do see relativity, or this relative time dilation, but we see it more in satellites. If you talk about a geosynchronous satellite, it turns out that a geosynchronous satellite has to be updated. I think it's either once a day or once a month, or maybe even once a week, because it's off. The clock runs differently on the geosynchronous satellite than it does on the Earth. So what it does is that over a course of a day or a week or a month, I can't remember exactly which one, it's off by something like a millisecond. Not a significant measurement of time. And a geosynchronous satellite is traveling around the Earth. It's making one loop around the Earth every day. That's why it's geosynchronous. As the Earth rotates, so does the satellite. So, looking at rotational motion, you should be able to see, even uniform circular motion, that it has a tremendously high velocity. And it takes an entire day or an entire week to build up a time dilation of one millisecond. I mean, we don't feel 1 millisecond. We don't see an event happening within a millisecond. I mean, our cognitive abilities are not there. We don't recognize that small of a time value. And the same thing goes for the length contractions. To see a length contraction, you have to have an incredibly fast velocity. Okay? So that's why we don't see relativity daily. I mean, we do, but we don't. It's just not significant enough. But I mean, it's just kind of an interesting phenomenon to have. I'm losing my train of thought. But I guess I'll just end it. This is our two equations that we're going to use for motion. We're going to use our time dilation. We're going to use our length contraction. The next time we'll talk about relativity is in momentum. One thing I did want to mention is that we tend to think of this relationship. Sorry, gosh, my brain is fried. Of 1 over the square root of 1 minus v squared over c squared is recurring. We see it over and over again when dealing with relativity. So we tend to give it its own symbol. This symbol right here representing gamma. Now, if you look at it, there's no unit there because velocity and the speed of light are both in units of meters per second. There's no unit floating around in here. So gamma is just considered to be a relativity correction. It doesn't give me a unit correction. It just gives me a scaling correction. Okay? Cool? So the other way in which you can see the time dilation equation is that you can look at it this way. T is equal to T gamma, or the length contraction equation being L is equal to L over gamma. Okay, and it's reoccurring. It shows up over and over again when you're dealing with relativity. When we look at momentum, we'll see it again. When we look at energy, we'll see it again.